Before we begin our journey into the deepest mystery of existence itself, I have a question for you, one that I'd love to hear your thoughts on in the comments below. If you could ask the universe one question and receive a definitive answer, what would that question be? Perhaps it's something about consciousness or the nature of time, or maybe something entirely personal about your place in the vast cosmic story. Tonight, we're going to explore perhaps the most profound question humans have ever asked. What existed before the very beginning of everything we know? What was there before the Big Bang? It's a question that sits at the intersection of physics and philosophy, of mathematics and imagination. So find yourself a comfortable position, let your breathing slow and deepen, and imagine yourself floating weightlessly in the perfect darkness of space. Not the cold emptiness you might expect, but a warm, enveloping darkness that feels like the most comfortable blanket you've ever known. Here in this peaceful void, we'll explore the gentle mysteries that lie beyond the edge of time itself. To understand what might have existed before the Big Bang, we must first travel back to that singular moment when everything we know began. Imagine, if you will, that you're drifting backward through time, watching the universe gradually contract and cool around you. The stars grow younger, galaxies draw closer together, and the cosmic microwave background radiation that bathes all of space grows warmer and more intense. You're floating in a universe that's becoming smaller, denser, and hotter with each passing moment. The familiar constellations fade away as individual stars merge back into the primordial soup from which they came. Galaxies spiral backward into themselves, their elegant arms unwinding like cosmic flowers closing their petals for the night. As we continue this gentle journey backward through cosmic history, the temperature around us climbs steadily. What was once the cold vacuum of space becomes warm, then hot, then blazingly intense. The very atoms that make up your body begin to vibrate more rapidly, their electrons dancing in increasingly energetic orbits around their nuclei. At 380,000 years after the Big Bang, we encounter a soft, glowing wall, the moment when the universe first became transparent to light. Before this cosmic dawn called recombination, the universe was filled with a thick fog of free electrons and protons, as opaque as a London morning shrouded in mist. Light couldn't travel far before being scattered, creating a universe that glowed like the inside of a star, but remained forever hidden from view. Continuing our backward drift, we enter this cosmic fog. Here, in the warm, dense plasma that filled all of space, we encounter the first great mystery. Matter and energy exist in perfect democratic equality. There are no complex structures here, no planets or stars or galaxies, just a smooth, almost perfectly uniform sea of particles and radiation flowing together like honey mixed with sunlight. To truly appreciate the mystery of what came before the Big Bang, we must first understand what the Big Bang actually was, and perhaps more importantly, what it wasn't. Contrary to popular imagination, the Big Bang wasn't an explosion that happened somewhere in empty space. It wasn't a bomb going off in a pre-existing void, scattering matter outward into darkness. Instead, the Big Bang was the simultaneous appearance of space, time, matter, and energy, all emerging together in what physicists call a space-time singularity. Picture trying to understand the concept of north while standing exactly at the North Pole. Just as there's no direction more north than the North Pole, there's no moment more before than the Big Bang, at least not in any conventional sense we can easily grasp. Time itself began with the Big Bang. Not time as we experience it in our daily lives, the steady tick of clocks and the gentle progression from morning to evening, but time as a fundamental dimension of reality, woven together with the 3 dimensions of space into what Einstein showed us is a unified fabric called space-time. This fabric is remarkable in its flexibility. It can stretch, compress, ripple, and bend. During cosmic inflation, a brief period just after the Big Bang when the universe expanded faster than the speed of light, space-time itself stretched so rapidly that regions of the universe that were once in contact were suddenly separated by vast distances, like dots on a balloon being inflated at tremendous speed. The mathematics that describe this early universe become increasingly strange as we approach what physicists call Planck time, approximately 10⁻43 seconds after the Big Bang. This represents the smallest possible unit of time that has any meaning in our current understanding of physics. It's a duration so brief that light, travelling at its maximum possible speed, can only cross a distance smaller than a proton. At this Planck scale, the familiar rules of physics begin to break down. Quantum uncertainty becomes so dominant that space and time themselves become fuzzy and indeterminate. It's as if reality exists in a constant state of quantum foam, with virtual particles popping in and out of existence and space-time itself fluctuating like the surface of a turbulent sea viewed from an enormous distance. The story of how we came to understand the Big Bang is itself a gentle tale of human curiosity and persistence. In 1929, Edwin Hubble, working with the Great Mount Wilson telescope under the clear California skies, made a discovery that would forever change our understanding of the cosmos. He found that distant galaxies were moving away from us, and the farther away they were, the faster they were receding. This wasn't because we occupied some special position at the centre of the universe. Rather, space itself was expanding uniformly in all directions, carrying galaxies along with it, like raisins in rising bread dough. If you imagine yourself as an ant walking on the surface of that expanding dough, every other ant would appear to be moving away from you, and the more distant ants would appear to be moving away faster. Working backward from Hubble's observations, physicists realized that if the universe is expanding now, it must have been smaller and denser in the past. Following this logic to its ultimate conclusion led to the extraordinary idea that everything we can observe, all the matter and energy in the observable universe, was once compressed into a region smaller than a single atom. This compression wasn't just physical but temporal as well. The Belgian physicist Georges Lemaitre, who first proposed what would later be called the Big Bang theory, described it poetically as the day without yesterday. Moment when time itself began. The evidence for this cosmic beginning accumulated gradually, like morning dew forming on grass. In 1965, 2 radio astronomers named Arno Penzias and Robert Wilson were trying to eliminate a persistent background hiss from their sensitive radio antenna. No matter which direction they pointed their instrument, they detected the same faint microwave radiation. What they had discovered, quite by accident, was the afterglow of the Big Bang itself. The cosmic microwave background radiation that still bathes the entire universe in a gentle, nearly uniform warmth. This radiation tells us a beautiful story. It carries with it the fossil imprints of tiny density fluctuations that existed when the universe first became transparent to light. These microscopic variations in temperature and density, preserved like fingerprints in the cosmic background radiation, would eventually grow into the great web of galaxies we see today. More recently, observations of distant supernovae revealed another surprise. The expansion of the universe is not just continuing but accelerating. Something we call dark energy, making up about 60% of the total energy density of the universe, is driving this acceleration, pushing the fabric of space-time to expand at an ever-increasing rate. When we ask what existed before the Big Bang, we venture into a realm where our everyday concepts of causation and sequence begin to dissolve like morning mist. In the quantum world that dominated those earliest moments, the very notion of before becomes as elusive as trying to grasp a moonbeam with your bare hands. Quantum mechanics, that strange and beautiful theory that governs the behavior of the smallest particles, tells us that at the most fundamental level, reality is inherently uncertain. Particles don't have definite positions or velocities until they're measured. They exist in what physicists call superposition, simultaneously existing in multiple states, until the act of observation causes them to collapse into a single definite state. In the quantum foam that may have preceded our universe, space-time itself was subject to these quantum fluctuations. Imagine the surface of a perfectly calm pond, viewed from so far away that it appears completely smooth. But as you zoom in closer and closer, you begin to see tiny ripples, then waves, and finally, at the smallest scales, a constantly churning froth of activity where water molecules are in constant random motion. This is similar to what quantum field theory suggests about empty space. What appears to be perfect vacuum is actually alive with activity, virtual particles constantly popping into existence in matter-antimatter pairs, existing for the briefest possible moment before annihilating each other and disappearing back into the void. Some theories suggest that our entire universe might have begun as just such a quantum fluctuation, a random bubble of space-time that, instead of immediately collapsing back into nothingness, was sustained and amplified by the process of cosmic inflation. In this view, the Big Bang wasn't a unique event, but rather one bubble in an infinite eternal process of bubble formation, each bubble potentially giving rise to its own universe with its own physical laws and constants. One of the most elegant and mind-expanding ideas in modern cosmology is the concept of eternal inflation. Picture, if you will, a vast ocean of quantum energy fields, stretching infinitely in all directions. This ocean is not calm but constantly churning, with waves and currents of energy flowing through higher dimensional spaces we can barely imagine. In this primordial ocean, bubbles of space-time spontaneously form and expand. Most collapse almost immediately, existing for periods so brief they make the blink of an eye seem like an eternity. But occasionally, under just the right conditions, a bubble stabilizes and begins to inflate exponentially, creating what we would recognize as a universe. Our universe, in this picture, is just one such bubble, expanding and cooling as it grows larger. But the ocean from which it emerged continues to churn and create new bubbles. In regions we can never observe or reach, countless other universes may be forming, each with their own Big Bang, their own physical constants, their own evolution toward complexity or simplicity. This eternal inflation hypothesis suggests that what we call the Big Bang was not the beginning of everything, but merely the beginning of everything we can ever hope to observe. Beyond the edge of our own cosmic horizon, the process of universe creation continues endlessly, like waves breaking on an infinite shore. The mathematics of eternal inflation reveal something profound about the nature of infinity. In an eternally inflating multiverse, every possible quantum event, no matter how improbable, will occur infinitely many times. There would be infinite versions of Earth, infinite versions of you, infinite variations on the story of cosmic evolution. This raises beautiful questions about the nature of existence and identity. If there are infinite versions of you scattered across infinite universes, which one is the real you? The answer, perhaps, is that they all are, each a genuine expression of the quantum possibilities inherent in the fundamental structure of reality. Not all theories about what preceded the Big Bang involve eternal inflation. Some of the most beautiful alternatives suggest our universe is part of an endless cycle of expansion and contraction, like a cosmic heartbeat that has been pulsing for eternity. In these cyclic models, our current universe will eventually stop expanding and begin to contract. Over trillions upon trillions of years, all the matter and energy in the cosmos will gradually draw back together, eventually collapsing into a big crunch, the mirror image of the Big Bang. But rather than ending in complete destruction, this cosmic collapse sets the stage for a new Big Bang, a fresh cycle of expansion and evolution. The ekpyrotic scenario, named after the ancient Greek concept of cosmic conflagration and renewal, suggests an even more elegant possibility. In this model, our universe exists on a three-dimensional membrane, or brain, floating in a higher dimensional space called the bulk. Other brains drift through this bulk like lily pads on a vast cosmic pond. Occasionally, these brains collide with gentle universe-creating impacts. The energy released in such a collision would appear to us as a Big Bang. But from the higher dimensional perspective, it's simply the result of two cosmic membranes brushing against each other in the eternal dance of higher dimensional space. What's particularly beautiful about the ekpyrotic model is that it solves several puzzles about our universe without requiring the extreme conditions of traditional inflation. The uniformity of the cosmic microwave background, the flatness of space, and the absence of certain exotic particles all emerge naturally from the gentle collision of brains in higher dimensions. These cyclic and ekpyrotic models suggest that time might not have a beginning at all. Instead, the universe might be eternal, not in the sense of lasting forever into the future, but in the sense of having no ultimate origin point. Like a river that has been flowing since time immemorial, the cosmic cycle continues endlessly, with each Big Bang simply marking the transition from one cycle to the next. One of the most revolutionary ideas to emerge from the marriage of quantum mechanics and general relativity is the holographic principle. The notion that all the information contained within a volume of space can be encoded on its two-dimensional surface like a hologram that contains a three-dimensional image. This principle suggests something profound about the nature of reality itself. Just as a hologram can encode a three-dimensional scene on a flat surface, the entire content of our three-dimensional universe, every atom, every planet, every star, every thought you've ever had, might be encoded as information on a distant two-dimensional surface. In the context of what existed before the Big Bang, the holographic principle opens up extraordinary possibilities. Perhaps what we experience as the birth of space-time was actually the moment when information encoded on some higher dimensional boundary began to be decoded into the rich, complex reality we inhabit. Think of it like watching a movie. The film strip contains all the information needed to create the experience of motion and story, but that information only becomes a lived experience when it's projected and decoded by the projector. In a similar way, the holographic principle suggests that our entire cosmic history, from the Big Bang to the present moment, might be the projection of information that exists in a more fundamental form elsewhere. This leads to beautiful questions about the nature of existence itself. If our reality is holographic, then what is the nature of the screen on which we're projected? What is the source of the information that gives rise to our experience of space, time, matter, and consciousness? Some physicists have proposed that this fundamental information exists in a timeless realm, not before the Big Bang in any temporal sense, but in a deeper, more primary reality from which time itself emerges. In this view, asking what came before the Big Bang is like asking what's north of the North Pole, a question that assumes a framework that doesn't actually apply to the situation. As we probe deeper into the mystery of cosmic origins, we encounter one of the most profound puzzles in all of science: the role of consciousness in the quantum mechanical description of reality. The standard interpretation of quantum mechanics suggests that the act of observation plays a fundamental role in determining the properties of quantum systems. This leads to a beautiful and mysterious question. If consciousness is required to collapse quantum wave functions and determine the properties of reality, how did the universe exist before conscious observers evolved? This is sometimes called the quantum measurement problem, and it touches on the very deepest questions about the relationship between mind and cosmos. One possible answer is that consciousness itself might be a fundamental feature of reality, present from the very beginning rather than something that emerged later through biological evolution. In this view, what we call the Big Bang might have been the moment when cosmic consciousness began to observe itself, causing the quantum potentials of the primordial universe to collapse into the definite reality we experience. This idea resonates with ancient philosophical traditions that see consciousness as the ground of all being, but it's also supported by some interpretations of modern physics. The mathematician and physicist Max Tegmark has suggested that consciousness might be a fundamental property of certain types of information processing, present wherever complex patterns of information flow and integrate. If consciousness is indeed fundamental, then the question of what existed before the Big Bang becomes deeply intertwined with questions about the nature of awareness itself. Perhaps what preceded our universe was not empty void or quantum foam, but rather pure consciousness, a cosmic awareness waiting to dream itself into existence as space, time, matter, and energy. This perspective transforms the Big Bang from a purely physical event into something more like a cosmic awakening, the moment when universal consciousness began to experience itself as the rich, complex, evolving cosmos we inhabit today. There's something almost magical about the way mathematics describes the deepest workings of reality. The equations that govern quantum mechanics, relativity, and cosmology don't just approximate how the universe behaves. They seem to capture something essential about its very nature. This has led some physicists to propose that mathematics isn't just a tool we use to understand the universe, but is actually the fundamental substance from which the universe is made. In this mathematical universe hypothesis, what existed before the Big Bang was pure mathematical structure, abstract patterns and relationships existing in a realm beyond space and time. The Big Bang, in this view, was the moment when one particular mathematical structure began to experience itself from the inside, creating the subjective experience of physical reality. Consider how a mathematical equation exists independently of whether anyone is thinking about it. The relationship expressed by EXMC2 was true before Einstein discovered it, and it will remain true long after humans have disappeared from the cosmic stage. These mathematical truths exist in what Plato called the realm of forms, a timeless domain of perfect abstract entities. If the mathematical universe hypothesis is correct, then our cosmos might be just one solution to a vast set of cosmic equations, one particular way that abstract mathematical relationships can be organized into a self-consistent whole. Other solutions to these equations would correspond to other possible universes, each with their own physical laws and constants. This mathematical perspective on cosmic origins is deeply beautiful because it suggests that the universe is not arbitrary but follows from logical necessity. The particular combination of physical constants, fundamental forces, and geometric properties that characterize our cosmos might be the only mathematically consistent way for a universe like ours to exist. In this view, asking what came before the Big Bang is like asking what comes before the number 1 in the sequence of natural numbers. The question assumes a temporal framework, but the mathematical structures from which reality emerges exist outside of time altogether, in a realm of eternal logical relationships. As we contemplate the possible origins of our universe, we cannot ignore one of the most profound puzzles in cosmology: the apparent fine-tuning of physical constants that makes complex structures, stars, planets, and ultimately life possible. The fundamental forces, particle masses, and cosmic parameters seem to be balanced with extraordinary precision to allow for the emergence of complexity and consciousness. If the strong nuclear force were slightly weaker, atomic nuclei would fall apart and stars could not shine. If it were slightly stronger, hydrogen would fuse so readily that stars would burn out before planetary systems could form. If the electromagnetic force were different by even a small fraction, atoms could not exist in stable configurations. The expansion rate of the universe itself appears to be fine-tuned to an extraordinary degree. If the initial expansion had been slightly faster, matter would have dispersed too quickly for galaxies to form. If it had been slightly slower, the universe would have collapsed back in on itself before stars had time to cook the heavy elements essential for rocky planets and biological complexity. This apparent fine-tuning leads to several possible explanations, each with profound implications for understanding what might have existed before the Big Bang. The anthropic principle suggests that we observe these finely tuned parameters simply because we exist to observe them. In a multiverse containing countless universes with randomly varying physical constants, only those rare universes with the right combination of parameters would develop observers capable of noticing the fine-tuning. This anthropic reasoning transforms the question of cosmic origins. Rather than asking why our particular universe has exactly the right properties for complexity and life, we might ask, in what kind of cosmic system would observers inevitably find themselves in universes with apparently fine-tuned parameters? The answer might be an eternally inflating multiverse, where every possible combination of physical constants is realized somewhere. From this perspective, what existed before our Big Bang was a vast space of possibilities. a cosmic laboratory where nature experiments with every conceivable set of physical laws. We find ourselves in a universe with life-friendly parameters, not because our universe was specially designed, but because only observers in life-friendly universes would be around to notice the apparent coincidences. It's a beautiful example of selection bias operating on the largest possible scale. One of the most ambitious attempts to understand the fundamental nature of reality is string theory. The idea that the basic constituents of matter are not point-like particles, but rather tiny vibrating strings of energy. These strings are unimaginably small, vibrating in multiple dimensions of space that are curled up so tightly that we cannot directly perceive them. In string theory, what we perceive as different types of particles, electrons, quarks, photons, are actually the same fundamental strings vibrating in different patterns, like musical notes played on cosmic instruments too small to see. The particular pattern of vibration determines the properties we associate with type of particle, their mass, electric charge, and how they interact with other particles. But string theory requires more than the 3 dimensions of space we experience in daily life. Depending on the specific version of the theory, it needs either 10 or 11 total dimensions to be mathematically consistent. Where are these extra dimensions? They're wrapped up in complex geometric shapes called Calabi-Yau manifolds, existing at every point in our familiar 3-dimensional space, but curled so small that we can't detect them directly. The shape and size of these extra dimensions determine the physical constants we observe in our universe. Different configurations of the extra dimensions would give rise to different values for the strength of fundamental forces, the masses of particles, and even the number of spatial dimensions that remain large enough for us to experience. This leads to an extraordinary possibility. What existed before the Big Bang might have been a higher dimensional space filled with vibrating strings, existing in a state where all dimensions were on equal footing. The Big Bang could represent the moment when 3 spatial dimensions began to expand rapidly, while the others remained tightly curled, creating the 4-dimensional space-time we inhabit. In this string theory picture, our universe is like a 3-dimensional slice through a higher dimensional reality. Just as a 2-dimensional being living on the surface of a sphere might be unaware of the full 3-dimensional nature of their world, we might be unaware of the additional dimensions that surround us at every moment. Some versions of string theory suggest that multiple 3-dimensional slices could coexist in the higher dimensional space like parallel sheets of paper in a vast cosmic filing cabinet. These parallel universes, or brains, could occasionally interact, and such interactions might appear to us as Big Bang events, the birth of new universes, or the collision of existing ones. While string theory attempts to unify quantum mechanics and general relativity by proposing that matter consists of vibrating strings, another approach called loop quantum gravity takes a different path. Instead of focusing on the fundamental constituents of matter, loop quantum gravity examines the structure of space-time itself at the smallest possible scales. According to this theory, space is not infinitely divisible, but is made up of discrete units, tiny loops of space that cannot be subdivided further. At the Planck scale, space-time becomes granular, like a digital image that reveals its pixelated structure when you zoom in far enough. In loop quantum gravity, the Big Bang was not a moment of infinite density and temperature, but rather a quantum bounce, a transition from a previous phase of cosmic contraction to the expansion we observe today. The universe in this view has been bouncing back and forth between expansion and contraction for eternity, with each bounce corresponding to what we would perceive as a new Big Bang. This quantum bounce occurs when the density of matter and energy approaches but never quite reaches the Planck density, the point at which the discrete structure of space-time becomes apparent. Quantum effects prevent the universe from collapsing to a true singularity, instead causing it to rebound like a cosmic rubber ball bouncing off an invisible floor. What's particularly beautiful about the loop quantum gravity approach is that it suggests a natural resolution to the singularity problem that plagued earlier models of the Big Bang. Instead of requiring initial conditions to be specified by hand, the theory predicts that certain features of our universe, such as its large-scale uniformity, emerge naturally from the quantum properties of space-time itself. The discrete structure of space in loop quantum gravity also provides a natural explanation for cosmic inflation. As the universe bounces from contraction to expansion, the quantum fluctuations in the granular structure of spacetime get stretched and amplified, creating the density variations that eventually grow into galaxies and galaxy clusters. In this picture, what existed before our Big Bang was not nothingness or pure potential, but a previous cosmic epoch, a universe much like our own, that had reached maximum expansion and begun to contract. The quantum bounce that created our expanding universe was preceded by eons of cosmic evolution, stellar birth and death, and perhaps even the rise and fall of countless civilizations. Our exploration of pre-Big Bang physics brings us to one of the most profound puzzles in modern theoretical physics, the black hole information paradox. When matter falls into a black hole, what happens to the information that describes its quantum state? Stephen Hawking's work on black hole evaporation suggested that this information might be permanently lost, but quantum mechanics insists that information must be conserved. Recent developments in theoretical physics suggest a surprising connection between black holes and the birth of universes. Some models propose that when a matter collapses to form a black hole, instead of creating a singularity, it triggers the formation of a new universe that expands into a space we cannot observe. From our perspective outside the black hole, the collapsing matter appears to freeze at the event horizon, gradually fading from view as its light is red-shifted into invisibility. But from the perspective of the matter itself, it passes through the horizon and enters a new realm of expanding space-time, essentially experiencing what we would recognize as a Big Bang. This black hole cosmology suggests that our universe might have been born from the collapse of matter in a black hole existing in some parent universe. What we call the Big Bang would have been the moment when this collapsing matter passed through the event horizon and began expanding into the space-time we now inhabit. The beauty of this model is that it provides a natural mechanism for universe formation that doesn't require the extreme initial conditions typically associated with Big Bang cosmology. The smoothness and uniformity of our cosmic microwave background could be explained by the fact that all the matter and energy in our universe was once confined within the event horizon of a black hole, where quantum effects would naturally create the correlations we observe. This picture also suggests a fractal-like structure to cosmic evolution. Just as our universe contains black holes that might give birth to new universes, the parent universe from which we emerged would contain countless other black holes, each potentially spawning its own cosmic offspring. The result would be an infinite family tree of universes, each generation arising from the gravitational collapse of matter in the previous generation. In this model, asking what existed before the Big Bang is like asking about the parent from which we inherited our cosmic DNA. Our universe would be one branch on an infinitely branching tree of cosmic evolution, connected to its ancestors and descendants through the mysterious physics of black hole interiors. As we contemplate cosmic origins, we cannot ignore the profound mystery of dark energy and dark matter, the invisible components that make up roughly 95% of our universe. Dark matter, comprising about 27% of the cosmic energy budget, reveals itself only through its gravitational effects on visible matter. Dark energy, making up about 68% of the universe, drives the acceleration of cosmic expansion. The nature of these dark components profoundly affects our understanding of what might have existed before the Big Bang. If dark energy is truly a property of empty space itself, a cosmological constant that represents the intrinsic energy of the quantum vacuum, then it might provide clues about the fundamental structure from which our universe emerged. Some theories suggest that dark energy is not constant but varies over cosmic time. In these models, what we observe as dark energy today might be the remnant of a much more powerful field that drove cosmic inflation in the early universe. This inflaton field, as it's called, would have dominated the energy density of the universe during its first moments, causing space to expand exponentially before decaying into the particles and radiation we observe today. The connection between inflation and dark energy suggests that the force currently accelerating the expansion of our universe might be the same force that created the universe in the first place. This would mean that what existed before the Big Bang was a state of pure potential energy, a quantum field existing in a metastable vacuum state, waiting for the right fluctuation to trigger its decay into ordinary matter and radiation. Dark matter presents its own mysteries. If dark matter particles were created during the Big Bang, they carry information about the conditions that existed in those first moments. The particular properties of dark matter, its density, its interaction strength, its distribution throughout space, provide constraints on theories about cosmic origins. Some models suggest that dark matter might not have been created during our Big Bang at all, but might be a remnant from a previous cosmic epoch. In cyclic universe models, dark matter could be the cosmic memory that survives from one cycle to the next, carrying information about previous universes forward into each new cosmic incarnation. The interplay between dark energy and dark matter also affects the ultimate fate of our universe, which in turn influences our understanding of cosmic origins. If dark energy continues to accelerate expansion, our universe will eventually enter a state of exponential expansion similar to cosmic inflation, possibly triggering the formation of new universes through quantum fluctuations in the vacuum. As we drift here together, in the gentle darkness of contemplation, surrounded by the profound mysteries we've explored, there's something deeply moving about humanity's quest to understand cosmic origins. Here we are, temporary arrangements of atoms that were forged in ancient stairs contemplating the birth of time itself. The question of what existed before the Big Bang reveals something beautiful about the nature of existence. Whether our universe emerged from quantum foam, cyclic bounces, colliding brains, or mathematical necessity, each possibility suggests that reality is far stranger and more wonderful than our everyday experience might lead us to believe. Perhaps what's most remarkable is not that we don't have a definitive answer to what came before the Big Bang, but that we can ask the question at all. In a cosmos where conscious observers are rare and precious, we represent the universe's attempt to understand itself, temporary patterns of organized matter and energy that have become aware of their own cosmic context. The uncertainty inherent in these cosmic questions is not a failure of science, but a profound reminder of the mystery that surrounds us. Each theory we've explored tonight, eternal inflation, cyclic models, holographic principles, quantum gravity, offers a different window into the fundamental nature of reality. They remind us that existence itself is far more creative and surprising than any human imagination could have conceived. In contemplating cosmic origins, we touch something eternal within ourselves. Whether time began with the Big Bang or extends infinitely into the past, whether we live in one universe or an infinite multiverse, whether consciousness is emergent or fundamental, these questions connect us to the deepest mysteries of being. As you prepare for sleep tonight, carry with you this sense of wonder at the sheer improbability and beauty of existence. You are made of star stuff, participating in the universe's ongoing process of self-discovery. Your thoughts and dreams are part of the cosmic story, temporary but precious expressions of the same creative force that brought forth galaxies, stars, and planets, all from the quantum depths of space and time. And so we return from our journey to the edge of time, carrying with us not answers but better questions, not certainty but deeper appreciation for the mystery that surrounds us. The universe that began 13.8 billion years ago, or perhaps has been cycling forever, or perhaps is just one bubble in an eternal multiverse, continues to expand and evolve around us, each moment bringing new possibilities into existence. As you settle into sleep, imagine yourself once again floating in that warm, enveloping darkness where our journey began. But now this darkness is not empty. It's pregnant with infinite potential, alive with quantum possibilities, resonating with the gentle vibrations of cosmic strings or the discrete loops of space and time. You are cradled in the same cosmic womb from which space, time, matter, and consciousness first emerged. Whatever existed before the Big Bang, whether eternal inflation, cyclic bounces, or pure mathematical possibility, it continues to exist within you, around you, and through you. You are not separate from the cosmos, but an intimate part of its ongoing creative expression. Rest now in this knowledge, letting the profound mysteries we've explored tonight settle into your dreams like distant starlight. Tomorrow will bring new questions, new discoveries, new opportunities to participate in the universe's eternal quest to understand itself. But for now, simply be present to the miracle of existence itself, the impossible fact that anything exists at all, including you, including this moment, including the vast and beautiful cosmos that dreamed you into being. Sleep well, fellow traveller in space and time. The universe is dreaming with you.